I can share the morning recording, the same problems, but I'll record from this point. So you'll get 2 links to recordings today. All right. So we need the molar mass of iron 3 oxide. Can somebody Google that real quick? Iron 3 oxide. What is the molar mass of iron 3 oxide? Anybody? Don't be scared.
Is it 159.69?
It is. It is. So we got 25.13 grams over 159.69 grams per mole of iron 3 oxide. And that's going to give us moles of iron 3 oxide. All right. Everything has to be in moles. You cannot do any stoichiometric calculations without everything being in moles. Anybody got that number? So 0.157 moles. Right. This is indispensable right here. That relationship. Because if you got any of the two, you can solve for the third. So we've done that. So now we know our relationship between iron 3 oxide and CO, so we can exploit that now. So we're going to convert moles of iron 3 oxide into moles of CO. Right, all of these stoichiometric coefficients are nothing more than conversion factors. We can interconvert between any of those reactants and products using the balanced equation. So we can figure out Fe2O3 to CO. We can figure out how much Fe we're going to get, how much CO2 we're going to get. All of that we can figure out with these relationships. So what do I want to keep? I want this, right? I want to get rid of this. What is how am I going to set up that ratio? That 1:3 ratio that we just said that we could derive from that equation. What am I putting in the top? The question is, what am I putting in the top and what am I putting in the bottom? If I'm looking for CO and I have Fe2O3, what I'm looking for always goes in the top. What I'm trying to get rid of always goes in the bottom. Right, so this will be 0.157 mole times what? 3 moles of CO over 1 mole Fe2O3. And this is Fe2O3. All right, so we can cancel that. If you do that math, it's going to be 0.472 moles. All right, questions? Any questions so far? So we gotta work in moles, but then the question asks for mass. What mass of CO is required to react with 25.13 grams, which is a mass of Fe2O3. So now let's do that. So now that's the final step here. Convert moles to grams. And again, we need the molecular weight. Right, so grams over molar mass is moles. So moles times molar mass be grams. We just need to stick that number in. CO is 28 grams per mole. Right, 12 for carbon, 16 for oxygen. So this is 28 grams per mole molar mass. So all we do is now stick those numbers in. So the moles we got from up here 0.472 moles times 28 grams per mole. So moles are going to cancel. I'm left with grams, and it's 13.2 grams of CO. So what this is saying is that if we're in a lab and I ask you to run a reaction with iron oxide and carbon monoxide, which is a gas, to give me iron plus CO2. If I ask you to do that, and I said, I'm going to give you 25 grams of iron, you would have to figure out how much carbon monoxide to add. But you couldn't figure it out unless you had the balanced equation, right? Because they're not one-to-one. If they were one-to-one, then it would be easier because you could just take the number of moles of CO and convert it into grams. But because they're not one-to-one, you have to figure that out. And that's how this works. Literally every time you do an experiment, you're figuring out the mole-to-mole ratio so that you can do a reaction. And in organic, we call it equivalence. So it's like one equivalent. If it's one-to-one, then it's one equivalent or one equivalent, same number of moles, basically. But if it's 1-to-2, then it's one equivalent is a certain number of moles. And then you just multiply that by 2 if you react in 2 equivalents of the other substance. So that's how that works. And that's how you apply it. Let's do another one. I want to work on, we're going to work on another example. If there are no questions about this one. Are there any questions about it? All right, let's take another example. Let's start with gallium metal plus oxygen. That's going to go to gallium oxide. And we need to balance that. And the question for this one is, what mass of gallium oxide is produced from 29 grams of gallium metal? All right. What's the first thing we need to do?
Balance both sides.
Balance both sides. You can't do stoichiometry without balancing the equation. What would you do? Let's see here.
Wouldn't you put like a big 2 on the right side? So that way you'd have 4 gallium and 6 oxygen.
Right here.
You'd put on the right side for the coefficient.
Okay, so I'm gonna put a 2 right here. Okay.
And then you could put a 4 behind the gallium on the left side and a 3 behind the oxygen on the left side.
You murdering the balancing, bro. That's good. That's good. So you got 4 galliums, 6 oxygens. Over here, you got 4 galliums and 6 oxygens. Excellent. All right. So now it's balanced. So now we know our relationships. For gallium to oxygen gas is 4-3. For gallium to the product is 4-2. Oxygen to the product is 3-2. So the question asked me, how much of this am I going to get if I reacted this much gallium metal with oxygen? And it's, again, once we balance it, we need to, number one, right, we balanced it, which we've done. Second, find our relationships. So balance. What about, so this is what we're comparing, gallium to gallium oxide. That's what we're comparing. And based on the equation, there are 4 gallium metals here and 2, so 4 moles of gallium metal, 2 moles of gallium hydroxide. So this is going to be in a 4-to-2 relationship. Right? Or we can say that relatively 4 moles of this is going to be 2 moles of that. So we know the relationships. Now, what we need to do next is do what? We need to take gallium, the gallium metal that we have, and make it into moles. So convert grams to moles of gallium metal. What do we need for that? We have grams and we want moles.
You multiply by molar mass.
Well, you'll divide, right?
Divide, yeah, my bad.
Divide the gram, that's okay. We'll divide the grams that we're given by molar mass. So we're given 29 grams of gallium metal, and the molar mass of gallium is, since it's elemental, you can just get that number straight off the periodic table. If you have one handy, somebody tell me what that is.
I got 69.723.
All right, so 69.72 grams per mole. So let's do that math real quick. So it's 29 divided by 69.72, and that is 0.415, let's say 416 moles of gallium metal. So now we're good. We're ready to rock. We got our gallium metal in moles, and we can convert that number of moles literally to anything in this equation. The thing is, here we only got 3 terms. But if we had a 4-term equation where you have 2 reactants giving you 2 products, it doesn't matter which one of those other 3 you want to convert to, as long as you know the coefficients. So let's do that. So now let's take we're going to convert moles of gallium into moles of gallium oxide, right? And we do that with this relationship right here, right? So gallium is 4 moles, 2 moles of gallium oxide, but we want this, so that's what we're putting in the top. So let's say 2 moles of gallium 2 oxide divided by 4 moles of gallium metal times 0.416 moles of gallium metal, right? And again, we're trying to cancel out the moles of gallium to convert that into moles of gallium oxide. And we can do that. As long as the equation is balanced, we can find a relationship between those two, and it's cake. All right, anybody not following? Anybody got questions? Feel the water rising? Anybody? All right, so let's do that math real quick. So that's gonna be 0.416 basically divided by 2, because the 2 and the 4 can cancel. All right, hold up, I screwed that up. So this will be 0.208 moles of gallium oxide. All right, so that's that. All right, so we found the moles of gallium oxide. Now, the question asked us to do what? Find the mass. How do we do that? We're going to go from moles to grams, That'll be our final step. So it's going to be 0.208 moles times the molar mass of gallium oxide, which is 187.44 grams per mole. Right, and that's going to cancel. We're going to be left with, let's see, times 187. .99 grams of gallium 2 oxide. Right. So any stoichiometric problem, you have to work in moles, and you can interconvert between moles and whatever other unit you need, but you have to start out working in moles. Even if you're given grams at the beginning, you have to go back and work in moles. All right. So you have to do some conversions. So that means you need to know how to get to molar mass, which you can if you got a periodic table. You just add up the atoms and keep the coefficients in mind, not the coefficients, the subscripts in mind. So yeah, we can do that with any one of these. And this is a great segue to the next part of our discussion, which is dealing with limiting reactants. All right, so limiting reactant. So when you think about the limiting reactant in any given reaction, right, there are two ways to define it. One is I'm not gonna say substance. I'll say the reactant that's consumed first. Right. The second definition is the reactant that produces the least amount of product. Right. So those are two definitions for limiting reactant. It's the one that gets the reactant that gets consumed first, or it's the reactant that gives you the least amount of products. All right. So let's give an example. So if I have, let's say, A plus B going to F, right? And just for the sake of argument, let's say that A, there are 2 moles of A and 1 mole of B, right? And when these two react, let's assume that F is formed, the reaction goes to completion, right? So everything gets used up. When you look at A and B, if you used up the 1 mole of B, how many moles of A would be left over? So if they're reacting together, and you react 1 mole of B and 1 mole of A to give you 1 mole of F, how much A is left over? If you start with 2 moles.
Just one.
Just one. It's 1 mole left. So B would get used up first. Right, that's going to get consumed first because there are 2 moles here after the reaction. All right, there'll be 1 mole remaining. So the B would be considered limiting. And then A would be considered excess. So limiting and excess. Those are two terms that go together. If one of those is your limiting reactant, the other one by default is the excess reactant. So if, and this is if if 1 mole of A reacted with 1 mole of B, you will get 1 mole of F with 1 mole of A left over. So one is limiting, one is excess. Let me give you another example. Let's say I'm building, I don't want to do this. Let's say I'm building a house. This is a crappy looking house, so don't trip about the drawings. So every house has 2 windows and 1 door, right? The wood and all that stuff, I'm not gonna get that deep in the weeds with it. But let's say for every house, you need 2 windows and 1 doors. And let's say you wanted to build 3 houses, right? You would need how many windows? So each house required 2 windows and 1 door. So if I wanted to build 3 houses, I would need what, 6 windows and 2 doors? Is that right? Yeah. Now,
Yes, sir.
what if you
I'm
had,
sorry.
I mean, that's okay. Let me put some panes in here so we can tell them apart. What if you had 4 windows and 2 doors? How many houses could you build if you only have 4 windows and 2 doors? Let me label them just in case you go back and look at the notes and ask, what the crap is that? So this is windows, and these are doors. All right. How many houses could you build if you have 4 windows and 2 doors? Actually, let me
2, right?
You can only build 2. Let me make this make more sense. Let's say you have 5 windows and 3 doors. All right. So with the actually, no, let me leave off a door because it's not, I need to make this make sense. So if you got 5 windows and 2 doors, you could build how many houses now? You could still only build 2 houses, right?
Yes, sir.
How many windows do I have left? So this will only be able to construct right? Only make 2 houses with 1 window left over. Is that right? So what can we say is limiting in this case? It's not the windows, because we got one window left. And if we found another one, we can at least put windows in a third house. But once we build those 2 houses, all of our doors are gone, right? So in this case, the doors are limiting, right? And the windows are excess. Just a way to think about it. Same way about if we're making bologna sandwiches. Y'all probably don't eat bologna, but I'm just using that. I ate a lot of it in college, but I'm just using that as an example. And I need 2 slices of bread for every sandwich, and I have enough bologna to make 10 sandwiches. So that's 10 slices of bologna, but I only have 8 slices of bread. When that bread runs out, I can't make any more sandwiches. So the bread is going to be limiting. The bologna will be in excess, like that. So that's how this works. Once the reagent, whichever one it is, once it runs out, then you can't do, the reaction stops. All right, so once the limiting reagent runs out, that's the end of the reaction. Right, we actually have a lab scheduled to do limiting reagent. It's a really cool lab too. I think it's like calcium oxalate and potassium chloride, or calcium chloride and potassium oxalate, and it gives you calcium oxalate plus potassium chloride. And the calcium oxalate is not soluble because oxalate is one of those polyatomics that's not soluble with anything except group 1 and ammonium. So once the reaction happens, you get a precipitate of calcium oxalate, and then you get to determine which is limiting and which is excess by either adding in some calcium oxalate to see if you get more precipitation, or adding in some add in some calcium chloride to see if you get more precipitation, or some potassium oxalate to see if you get more precipitation. So that's a real cool reaction. I think we're going to be doing that on next week. All right. So with that being said, let's look at this in a practical sense and look at an example. All right. So we have a reaction here, and it is silicon plus nitrogen gas going to silicon 3N4. All right. Is that balanced?
No.
No. So let's balance it. What would you do?
Put a 3-bond to silicon and a 2-bond to nitrogen.
Good. So now it's balanced. So now we got our stoichiometric, we can use these for our stoichiometric relationships. So the question is, which one of these is limiting? So it's silicon because it's limiting reactant. It's not having it to have anything to do with the products other than products being formed. So it is, if I start with 2 grams of silicon and 1.5 grams of nitrogen, the question is which is limiting. All right, let's find that out. Everything has to be in moles. So let's turn 2 grams of silicon into moles. Silicon has a molecular weight or atomic mass of 28.09. So let's do that. So that's going to be 2 grams divided by 28.09 grams per mole for silicon. And for nitrogen, it also is, since it's diatomic, it's going to be 28. So it's going to be 1.5 grams divided by 28 grams per mole. All right. When we do that math, this comes out to be 0.0712 moles. And this comes out to be 0.054 moles. Right. So now we need to figure out how much product silicon will generate and how much nitrogen will generate. So now we know that, we can figure out which one is limiting. So how much product will each generate? I'll say produce. I know that's redundant, but I'll say produce. How much product will each produce? So we can figure that out, right? We know the relationship between silicon and the product is 3:1. The relationship between nitrogen and the product is 2:1. And we want product in the top. So we're going to say for silicon, it's going to be 1 mole of Si3N4 divided by 3 moles of silicon. You want to get rid of that times the amount of silicon in moles, which is 0.712. And we want to say the same thing. One it is 4 moles, all right, of nitrogen. 4 moles of N2. All right, or 2. No, it's 2. Yeah, it's 2, my bad. This is 2 moles N2 to 1 mole Si3N4 times 0.5054 moles N2. Which one of those is going to give me the smallest number? Once we figure that out, then we'll know which one is limited. Right, so all we're doing is taking the balanced equation and using the relationships in the balanced equation to tell us about product formation. Anybody got the answer yet? And that's not 712, I'm sorry, it's 0712. Anybody got it yet? Right, so for silicon, it is 0.0237 of silicon. For nitrogen, it is 0.0268. So nitrogen is going to give me this much product, and then silicon is going to give me this much. Which one is the least amount?
The first one.
Silicon. 0.0237 is less than 0.0268. So this is limiting. This is going to give me the least amount of product. And then this is by default excess with, let me see, 0.0031 moles left over. Right, all I'm doing to find out how much excess is just subtracting out what's limiting from the other one. So 0.0237 minus, or 0.0268 minus 0.0237 is going to give me 0.0031. All right, any questions about that, about limiting, reactants, about anything we've done so far? I apologize for going over a little bit. We'll finish out this on Wednesday, talk a little bit about titration and theoretical yield, calculating yields, and then we're gonna move on to another section. All right, everybody good? Anybody have any questions? All right, well, have a good afternoon, and I'll see you back on Wednesday.
You too. Have a great day.
Okay, take care.
Oh, I got a question.
Come on.
So I emailed you about the organic chemistry stuff. Can I just email it to you?
So let me ask you a question. Are you also taking organic?
No, I'm not taking organic.
Oh, so you want a tutorial on that to kind of bring you up to speed?
Yeah, because I was going I'm a junior, so I need to I'm gonna take these. I got to take like a little more underclassmen stuff, and then I'm gonna be about ready to graduate. I think I got like 12 more classes left.
Okay. Yeah, you can send it to me. Send it to my personal email address. Let me put it in the chat. Because when I saw your email, I thought that you were in my organic class. I know I recognize the name. I'm like, but that's okay. Yeah, send it to this email address.
All right, thank you.
No problem.
Do you know when we're gonna get the grade for our last test?
The test 4?
Yeah.
Well, test 3, I graded. Oh no, I haven't graded for section 2 yet. I graded section 1 last night. Between today and tomorrow, everything is going to be graded.
Okay. And when is our recitation due?
You can turn it in today. Have you taken the test 4 yet?
No, I haven't taken it. I'm gonna
Yeah.
take it.
Yeah, you can just turn it in after you take that test or before you take it. It don't matter.
Okay, thank you.
You're welcome. Have a good day.
You too.
All right. Oh.